There we go. Morning all. So welcome to today's double header. Didn't let you know about that before you joined. We will be covering chapters 4 and 5 today.
Yay.
There'll be double headers for basically the rest of the term. They're not very big. They're about 30 odd slides each. So some are 20, some are 30. So we'll get into it and kick off with the physical layer characteristics. So we'll look at what characteristics are in the physical layer and then look at the various media that reside in the physical layer. So you kind of can gather from the name that it's physical equipment, so you can touch it and feel it, whereas when we start moving up into the other layers, you know, it's all software. You can't really see what's going on. So we'll be looking at how to make physical connections and how the network interface cards interface with the physical world, and the fact that not all media types are the same. So for strange reasons, some perform better than others. It's a bit like apples and oranges. It comes down to the personal preference and selecting the one that does the job. So what is the purpose of the physical layer? It is responsible for transporting the bits from point A to point B. Okay, so we encapsulate the frame and put it onto the wire in ones and zeros. Now, how we represent those ones and zeros is dependent on the type of media that we're using. So, standards that occur at this layer are governed by the usual suspects: ISO, ITUT, IEEE, there was a whole chapter that had big spiel on organisations and standards and that. I'm sure you haven't purged it out of your memory yet. Or read it.
Yeah.
So the three functional areas within the physical layer are the physical components, how we encode the frame, and how signaling occurs. So how we make the ones and zeros go across the hardware. All right, so we'll look at the various materials used in getting that signal from point A to point B. So let's start off with encoding. So encoding is the method that we use to represent zeros and ones. And we use various methods to get this across. So the first one here, we talk about the Manchester method, which is basically a voltage change. Okay, so when it's above the carrier signal, it's a 1. When it's below it, it's a 0. So that's roughly how we represent. Now, this signal wave, the square wave here, digital signal, is what it looks like in theory. It's not what it actually looks like in practice. What it is in practice is like this. Okay, see how it's all jagged and horrible and not a clean signal like this one? This is because there's very many, it's not very, there are many things that contribute to the interference of a signal across the cable. So there's, variations in like the copper quality. There's outside interference from electrical motors, electrical cables, fluorescent lights. All of these things can contribute to noise within a cable. And that's why we get such a ragged looking signal. Now, the way signaling works is we have a base carrier normally, which we then impose the signal on top of to get transport. Okay, so when you look at plugging in a cable, within a few seconds the cable indicator lights turn green. We're not transporting any data at that stage. We are just connecting a circuit, and that circuit has a base signal that maintains the circuit, that we then put the information that we want to be transported on top of. So how does this look in the various formats? Top one, light pulses over fiber. So the intensity of the light changes to represent ones and zeros. If we come down to radio, I know it's gotten out of fashion with you youngsters, but we used to have these things called AM and FM radio channels.
I know what they are. The FM radio channels, though, are like really, really old.
Not as old as the AM ones.
No, the AM ones are old. I still listen to FM radio in the car.
Yeah, most people probably still do.
I like Gold FM.
Basically, what the differences are is the way the signal's sent. So AM means amplitude modulation. So it changes the peak and troughs to represent the ones and zeros. FM is frequency modulation, so how frequent the peaks are. That's what frequency is. If you remember the old physics, and you're all going, physics classes, I purged that. All right, so frequency change, so the more frequent the signal represents a 1 within a certain time frame. And then phase modulation is we basically 180 the wave. So we change the direction of the wave in phase modulation, which is PM. So here we have it going up, and then we change the phase, so it turns and starts going down.
Does that mean we could use that and cook our eggs?
Can you cook eggs? Any radio frequency, if you expose yourself to it often enough and long enough, will cause some change.
Okay. Well, that's reassuring.
That's what all the big... we saw the usual conspiracy theories come out with 3G, 4G, saying, you know, it's going to cook us, it's going to, you know, make us all zombies. And to some degree that has occurred. Everybody's nose down in their phone walking around. But 5G, that it's just the same old, you know, it's going to kill us, it's going to be, you know, fry us and all that. It just rolls out every time they bring out a new generation. So, how we represent bandwidth on the physical medium is in bits per second, and it's based on, you know, decimal. So it's not binary. So it's a standard ISO measurement. So it's, you know, kilo being 1,000, mega being 1,000,000, giga being you know, 1,000 million, and then tera being a million. So bandwidth terminology, we have latency. This is the amount of time it takes to get from one point to another. So for every device that you go through, it adds a little bit of latency as it needs to calculate what to do with the traffic. Throughput is our actual measurement of our bandwidth. So how many bits travel across the media in a given time. And good put is Cisco's way of measuring the actual data that is transferred in that time. So throughput includes the data and any overheads that are needed to maintain the conversation. Good put is just the data. So the actual element that you're transporting is good put. So how much data you actually get across. Okay, copper cabling is the most widely used cable out there. It has limitations based on the physical characteristics of using copper cable. The longer the stretch of cable, the more resistant it becomes to having electrical power pushed through it. And this degrades the original signal. So the signal gets weaker as it gets further away from the source. And this is called attenuation. The electromagnetic interference and radio frequency interference, or crosstalk, are all types of extra signal that gets put into the cable. So EMI are from such things as motors, electrical motors running near the cables, high magnetic sources of power. Radio frequency are such things as your microwaves, that sort of thing, radios. And crosstalk is actual signal transfer between one wire and another within the cable. Okay, so when you push electrical signal, your electrons through the copper, they generate a magnetic field. Okay, and those magnetic fields, when you have wires laying on top of each other like you do in a cable, they cause interference in each other's field, and it can change the field on one to the other. All right, so you might have a 0, a normal flat signal going through cable A, but cable B has got something going on, and that magnetic field that is interfering with the first wire, and some of that will change the shape of the magnetics or the electrons' behavior in the wire. If you're interested in the mechanics of that, become an electrical engineer. Or do a photonics course. That's another fun one. That's fiber optics. They were interesting classes to take at uni.
Have you done electrical engineering?
Hey?
Have you done electrical engineering?
I've
Or was it just a...
started.
Okay.
Yeah, I've done bits and pieces. I actually started doing a dual degree in electrical engineering and photonics.
Okay.
So, yeah. And then I got accepted into my master's, so I just went and completed my master's.
No, that sounds fair.
I was bored, so I started the dual degree while I was waiting for acceptance into the master's, which took forever. So, yeah. But I actually started off my career in electrical design. I was an
Which is
electrical
laying
designer.
out.
So basically, I would do infrastructure design for schools, buildings, that sort of stuff. Industrial plants. So anything to do with motor controls, instrumentation, all that sort of stuff. I used to design and document and have an engineer sign off on.
That'd be kind of like that Adreno thing, wouldn't it? With that thing you can set up and you can make like arms that pick up stuff, and I feel like it's a kid's toy, but I feel like it's a similar concept.
There's lots of different elements within the discipline, just like there is with any other discipline.
That one.
Yeah.
Adreno.
Adreno? Okay.
You use like I feel like you have to code on like Raspberry Pi or something.
Yeah.
Yeah.
Basically coding a robot. Yeah. Okay. See, we used to, when first days of teaching, we used to teach coding using Lego.
Okay.
We used to make the remember the big tracks with the black tape? Have you ever saw those? And then you'd basically have a Lego ball or a Lego car that would have an optical sensor that would sense the black track.
Right.
Because you basically have a green board with a black tape track on it.
Yeah.
And the sensor would see the change in colour and it would follow the track, and you'd code how it behaved depending on the shape that it saw on the track. Another thing they used to do was play soccer with the robots. Yeah.
I remember
did that in a couple of colleges. So yeah. Robert, not so much. The fiber optics are relatively expensive when you're talking cabling. Copper cable is much more user-friendly as far as installation is concerned. It's cheaper and much more flexible and robust when you're talking about mechanical damage to the actual cable. So fiber optic cable provides more throughput and a certain guaranteed protection from interference, such as from motors and things like that. And it can go a further distance than what copper can. But yeah, you're not generally saying please use fiber. There is distinct areas where you just use fiber for the characteristics that fiber provides us. So yeah. All right, let's get back to this so we can get through it. The strict adherence to cable lengths, to be able to comply with the standards, we have to comply with the cable limitations that they put in, and that's all to do with signal strength and the integrity of the signal and the encoding. So basically the standards are written with certain timings in place, and if you put in an extra long cable, then that throws out the maximum time that a frame would be on a cable to get from point A to B. So if you run 130 meters of cable, the standard says 100 meter maximum, your signal strength at 130 meters would be hit and miss. It would still work, but it wouldn't be at the standard required. And because each frame would travel along that cable longer, because it takes extra time to get that extra distance, you would have extra collisions and things like that. So you'd have more bad events happening, basically. Crosstalk, one of the main ways we get around crosstalk in cables now is category 3 cables, they were just bundled together. There was nothing special about it, i.e. your standard telephone cable. Your category 5 and category 6 cables now twist pairs together at a different rate of twist per meter, and that stops the magnetic fields from interfering with each other because they wrap around each other. So they're always changing their positive and negative elements of their fields. And the other thing with category 6 cables, they put a physical barrier in between the pairs. So it limits the effect of the magnetic field by putting a solid barrier in its place. Another way you can do it is to actually put shielding in, i.e. the old foil. Okay, so unshielded twisted pair is your standard Cat5 cable, and you should be able to see how the rate of twist between the blue and the blue-white pair here differs greatly from the orange and orange-white. Hope that can be seen through there. So each pair has a different ratio of twist, and that cancels those magnetic fields out from each other, helping to eliminate crosstalk. And shielded twisted pair, you will have a outer shield around, and if it's a really noisy environment, you would have individual shields around each pair as well. Okay, and doesn't show up very well on this background, but they've got this solid shielding, which is basically a big plastic cross that runs along the center of the cable, and each little wedge has a separate pair residing in it. Coaxial cable, solid core, plastic sheath, and then a copper braiding over the top of that, which is your shielding, and then your PVC outer sheath, which is mechanical protection. So basically, what I just said, you've got your outer sheath, your individual twisted pairs, and we use a RJ45 connector on these devices to connect these cables to our devices, which is the large network cable plug that you've all seen and used on your home router. So outer sheath, physical protection from damages, and color coding so that we can identify which pins each wire connects to. And I've already talked about the shielding and the braiding on the other ones, so I'm not going to repeat myself as I've already talked about it. Okay, coax cabling has slightly different. It's basically just one pair. What we do is we use the solid core as one wire and the braid as a second wire. Okay, and they're physically separated via the insulation, and then the outer coating provides mechanical protection. And we attach them via the connectors. B&C is the most common connector, and I still have a chuckle when I hear the original or look back at the original versions of the Cisco course, because they talked about B&C being British naval connector. It was invented by the British Navy so that the cables wouldn't fall out. Because, good chuckle. All right, I'm showing my age. So B&C is just like the old light globes. They're a bayonet connector. So you push it in and give it a twist. Okay, it has the little prongs on it. N-type is a screw connector, and so is the F-type as well. Where would you normally use coax? It was first seen in households on aerials, antennas. So your TV antenna. So when you had the big aerial outside, you'd run coax in to your TV. Alright, so what's new on this slide? They're basically talking about the cancellation effect with the magnetic fields using the twist function, which I've already talked about. So moving on. And here's the representation of what I was talking about with Cat3 being just straight cables. So you would end up having crosstalk between the wires. The Cat5 started to twist the pairs, and that eliminated the type of interference that was occurring. Now, how we terminate the cable into the plugs is governed by TIA EIA standard 568, and basically we'll have a look at the 568A and B standards of termination, which determines the functionality of the cable, which we'll get to in a second. So the standard RJ45 connector looks like this. it's a little clear housing with copper pins at the top end that cut into the individual wires. This is what gives us our connection point between the plug and the socket. Okay, so to be in the old terms, your connector was a male and the socket the female, and the female has little fins hanging down that will brush up against these little plates on top of the connector. And the way it works is, as I said, these are like a pin that cuts into the wire, and on the socket we actually push the wire down into the socket connector. So let's see if I can. So this, you'll have, I'm using my mouse, you have the wire there which is made up of all these individual strands, and then you basically push, when you crimp these together, you actually push a V shape into the wire, and you make connections next to each other with the individual strands. So this transfers the electrical signal off the individual strands in the cable up through your copper pin that comes out to the outside of the plug. On this one, you have a basic V razor blade that you push your little wire down into, and it ends up cutting into the wire. So your individual strands will just end up in that V shape, or compacted up. Okay. Poorly terminated UTP means that the what constitutes poorly is, in this diagram here, we've got too much wire exposed. Okay, so they are no longer twisted. There's a fairly long stretch where the individual wires are not twisted together anymore, which introduces the possibility of cross-torque occurring. The mechanical sheath, outer sheath, is not in the plug, in the connector. So if you tug on the cable, you could actually pull the wires out of the connector. So in the bottom example here, back, thank you. Jeez. You'll see that the outer sheath is actually inside the connector, and when you clamp it together, this little area here of the plastic gets pushed down and squishes the actual cable together in the plug, and you only have enough individual wires exposed to get separation in the actual plug itself. Now, the way it works is we need an A and B plug if we want to create what's called a crossover cable. Crossover cables were generated from the old days, where we would have a transmit and a receive pin on our source and destination, our A and B. So when we transmit, we don't want the transmit going to the transmit pin. We want the transmit going to the receive, and then the receive going to the transmit, the crossover. Is that making sense? Okay. So the crossover occurs because we are swapping over pairs 2 and 3 within the cable. So if you look here, pins 1 and 2 are the green. Over here, they're the orange. So they swap. So that's our physical crossover between our transmit and receive pair within the cable. So we only need an A and a B if we want to create a crossover. Any other time, a normal patch lead is 2 A's or 2 B's, as long as they're terminated the same at both ends of the cable. That will be known as a straight through cable, i.e. a patch cable. Now, we don't tend to use crossovers as much now because we have this function called auto MDIX on new equipment, which will automatically detect the type of cable in use and the pins being used and do the changing of transmit receive in the electrical device that it's plugging into, rather than having it in the physical cable. A rollover cable, which is a flat blue cable. I really should have pulled one out of the box. Is a Cisco proprietary cable that they use as the base configuration cable. So this is the one that you plug into your laptop and into the equipment to do the initial configuration of a device. You cannot do that initial configuration via any other method. You must have a cable connecting it to the host, to the machine. Fiber optics is, as I said, not as widely used because it's more expensive to install. You need very specific equipment to do terminations, and if you have damages, it requires a lot more care taking to do repairs. High traffic areas, as in underneath desks and that, where things can come into physical contact with cabling, can cause damage. So fiber optics are more prone to mechanical damage than what copper cables are. And they do not bend very well because the early ones were basically pure glass. Okay, I'll have to find it again, but I used to have a little short video that I used to play. That's one of the things I lost. So basically the way they make it is they get 2 glass rods. One's a glass cylinder and the other one's a solid glass rod. So they'd slide it in between each other. And what would happen is the compound between one glass and another, they were slightly different mixes of glass. So they had slightly different transparency elements. And then they would blow a gas in between the gap and then put it on a long drop tower and melt the glass. And the glass would slowly melt and drop down this very long tower and become a very fine strand, which is how they then wind up you know, they meld it, put it on a big coil. It's quite fascinating to watch how they make it. Okay, so to get the light injected into that little fibre of glass, we use a high precision laser or a high precision LED light to inject the light source in to the end of the fibre. So we have two main categories of fibre, and that's single mode and multi-mode. And what the main differences are is in single mode, your core, which is the centerpiece, is a lot smaller than the multi-mode. So you've got 9 microns to basically 50 to 60 microns in multi-mode. So 5 to 6 times as large in multi-mode. What this allows us to do in multi-mode is to inject more sources of light, so we can have multiple colors, if you like, bouncing down a multi-mode fiber, allowing us to inject more data. Okay, so up to 10 gigabits per second, up to 550 meters in multi-mode. With single mode, we only basically use a single injection point, so one signal, but because it's only one signal and it won't interfere with each other, we can make it run a lot longer distance. I won't go into the whole mathematics of reflection and refraction. It's interesting for a little geek like myself. I enjoyed my photonics classes. I learned how our eyeballs worked. That was interesting. Optical. So they have to actually teach you the eyeball as part of the curriculum. So that's quite... yes, in regards to the amount of bandwidth that we effectively can push down through it, Brock, it is slower than multi-mode. The trade-off is we get kilometres of distance, like 2 kilometres plus with a single mode strand, compared to 500 metres with a multi-mode. So it's a trade-off. If we've got a long distance to go, we use single mode fibre to get the distance, but the distance comes with the cost of not having as much bandwidth. Okay, so common cabling usages is long-haul networks, submarine cables. Fibre to the home now is becoming a thing. It's a rip-off, in Australia at least. They bring one fibre strand to the house. What's that mean? It means it's half duplex. You can talk or you can listen. You can't do both. Light can only be injected into the cable in one direction at once. Okay?
Destined to be slow.
Yeah, so there we are. So in most instances, you will have a pair of fibre. Trouble is, if they didn't change the original plan, I don't think we'd have even what we have now. That's just the sharp reality of it, because no private corporations wanted to actually invest in the NBN. They want somebody else to build it and then rely on the ACCC anti-monopoly laws to force them to give them access to it. That's another debate. So Types of connectors: straight tip, subscriber connectors, duplex multi-mode, and Lucent connectors all have slightly different characteristics. So straight tip, you push the tip in and use like a BNC type twist, push and twist connector. Subscriber connectors were a little square and they basically push in and snug fitting, so they clip in. The Lucent and multi-mode Lucent connectors have the plastic lip here, the tongue, pretty much like the category 5 ones. So the normal network cables you're used to have that little tongue on it that you push in and it goes click. Same with the Lucent ELC connectors. So generally you have different types and different colors for representing the types of mode. So in this example we have yellow jacket for single mode and orange for multi-mode fiber. Now you can do special orders that have different colors for different types of cabling. For example, if you had color coding for, let's say, different levels of security, and you might have different color codes based on the security level of your installation, for example. Benefits of UTP compared to fiber optics. Well, fiber, you tend to get a higher maximum speed out of. The distance, copper is very short compared to what you can get out of fiber optics. The protection against outside interference is higher in fiber than it is in UDP, but that comes off with a trade-off against cost of installation. So copper is very low cost, fiber is very high cost, in that the media is more expensive, the skills required for the labour force are higher, so therefore you're paying more for those installers, and the safety precautions you have to take are higher because you're dealing with very fine micron bits and pieces of glass that when you cut you can get shards, and if they get into your bloodstream they can be transported in your blood up to your heart, and you know what happens at that stage. Little jaggers of glass going through that big pump doesn't end well for you. I'll just leave it at that. So you've got to be careful with fiber when you're doing it. Next media type is wireless. We all know wireless. We use mobile phones and Wi-Fi all the time in today's environments. So we are limited with the coverage area of the wireless medium depending on what type of wireless we're using. Wireless is also very much susceptible to interference. Now that could be from other devices. It could be as physical obstructions also. I like to highlight the fact that most people have dropped stones, pebbles into ponds and things like that and seen the ripples of water, and it's very much like that. Radio waves are like that, rippling through the pond. If you put an obstruction in it, that ripple gets disrupted okay, and changes the shape. I'm sure you've all seen that occur in your life. Wireless is inherently unsecure because it's a radio transmission and you don't control where it goes. All what you can control is the signal strength that you transmit. That's it. So, and because it's shared medium, everybody's trying to use it at the same time. So, two end devices might be at near maximum limits between the access points and themselves, which means they're twice the distance away from each other as what the standard calls for. So those end devices won't actually see each other and could transmit at the same time, causing more interference with signals. So again, wireless needs to conform to all sorts of encoding, signal standards, frequency and power of the transmission and reception, antenna designs. All these are governed via the IEEE standards. And when dealing with Ethernet, we will always start with 802, which is the Ethernet standard. And then the numbers after the dot point after that refer to the various media types used to transport Ethernet. So Wi-Fi is .11, and then you've got the A, B, G, N, so on and so forth that you're all used to. Bluetooth is 15, WiMAX, which is a broadband wireless service, is 16, and the new Zigbee, which is the Internet of Things, is a 15.4 because it's basically a modification of personal area networks because they're not supposed to be over a wide area. So wireless access points need a connection to the wired network to provide continuity between normal networking and radio transmission points. And on your devices, they need a wireless network interface card. Just make sure you are compliant at both ends. So an access point will provide connectivity over certain standards. Make sure your wireless network card complies with the standard, or else it won't talk to each other. So in summary, we had a look at how physical connections occur, what types of media is covered in networking, copper, fiber optics, and wireless. And we had a look at who's responsible for the controlling of the standards for the physical media. We had a look at the wiring conventions for straight through and crossover cables. We had a look at the main fiber optic connectors. We talked about the two standards of fiber optic cables. We then had a very brief overview of wireless standards. And that concludes chapter 4 of Isn't that good? You're going, yay, he finally shut up.
No, we still have chapter 5.
Yeah, we do.